a tunnel straight through the whole Earth, and a much shorter tunnel between two nearby cities both take exactly 42 minutes. Drop identical capsules into both, release them at the same instant, and they reach the opposite ends together. The long capsule travels almost 13,000 kilometers. The short one might travel only 3,000, same arrival time. That needs some rules. Make Earth a perfectly uniform sphere. Remove the air, remove friction, and let gravity do all the driving. No engines. The tunnels are straight cords with their ends on the surface. Now pick the winner. The diameter tunnel is much longer, so surely it loses. Except its capsule falls toward the center and becomes extremely fast. Fine. Then the short tunnel should win because it barely has anywhere to go, except its track never points very steeply downward, so gravity accelerates it weakly. Those effects could partially cancel. But exactly for every straight tunnel? That sounds suspiciously tidy. Here is the actual race. The diameter capsule dives through the center at nearly 8 kilometers per second. The short tunnel capsule makes a much less dramatic trip. Watch the progress bars though. 1/4 done, halfway, 3/4. They remain locked together and stop momentarily at their destinations after about 42 minutes. The obvious explanation would be that the shorter path gets proportionally weaker gravity. That is close, but it hides the strangest part. Inside the sphere, gravity itself is changing, and most of the planet stops contributing in a way I absolutely did not expect the first time I met this problem. So what gravitational force does a capsule actually feel underground? Underground, the capsule is not pulled by the entire Earth as though all its mass sat at the center. That shortcut only works outside a spherical planet. Once you are inside, split Earth into two pieces, a smaller sphere beneath you, and all the spherical shells surrounding you. Start with one thin outer shell. The nearby part of that shell pulls strongly because it is close, so I first guessed the capsule should be dragged toward the nearest wall, but there is more shell on the far side. Each far patch pulls less, yet a larger collection of patches lines up behind it. When all those pulls are added, they cancel exactly, not approximately. Anywhere inside a perfectly uniform spherical shell, its net gravitational pull is 0. That is the shell theorem, and it makes the outer part of Earth simply disappear from the force calculation. It is still there. It could still crush the tunnel, which our mathematical Earth is being very polite about. Gravitationally, though, only the smaller sphere closer to the center than the capsule matters. Now shrink the capsule's distance from the center by half. The active inner sphere has half the radius. Its volume, and therefore its mass, is 1/8 as large. But that mass is also only half as far away, making its pull 4 times stronger per unit mass. 1/8 times 4 gives 1/2. So, at half the radius, gravity is half as strong. At 1/3 the radius, it is 1/3 as strong. Gravity inside a uniform Earth is proportional to distance from the center. It points inward and fades smoothly to 0 at the center. That explains the diameter tunnel. Strong acceleration near the surface, none at the middle. But a shallow tunnel never approaches the center. Why should it obey the same clock? A shallow capsule does feel substantial gravity the whole time. Most of it is useless. Freeze the capsule somewhere along its tunnel. Gravity points toward Earth's center, but the tunnel only allows motion along one straight line. Split the gravity arrow into 2 components. One presses sideways into the track pushes back and cancels it. The other points along the tunnel, toward the tunnel's midpoint. That is the only component that changes the capsule's speed. Now mark the capsule's position along the track as x, measured from that midpoint. Here is the turn that makes the whole result work. The full gravitational arrow has a size proportional to the capsule's distance from Earth's center. But the fraction of that arrow lying along the tunnel is x divided by that same distance. Multiply them, and the distance from the center cancels. What remains is an acceleration along the tunnel proportional to minus x. Not the tunnel's depth, not its length, just the capsule's displacement from the midpoint, with the same constant of proportionality for every chord through this Earth. Written compactly, it is the equals minus g over r times x. The minus sign says the acceleration always points back toward the middle. At an endpoint, x is positive and the capsule accelerates inward. At the midpoint, x is 0, so the along-track acceleration is 0. Past the midpoint, x becomes negative and gravity slows the capsule until it stops at the other surface. Look at 2 different tunnels using their own midpoint coordinates. Stretch one picture until the endpoints line up. Their acceleration arrows match at every equal fraction of the journey. The tunnels differ in physical length, yes, but the rule governing their progress is identical, and that rule has a familiar motion hiding inside it. The capsule moves exactly like a weight on a spring. Pull a spring weight to the right, and the spring accelerates it left in proportion to its displacement. Release it, and it passes through the middle fastest, slows on the other side, and returns. Our capsule does the same, except gravity supplies the restoring force, and the spring is an entire planet. Slightly excessive laboratory equipment. This motion is called simple harmonic motion. Its feature is that changing the amplitude does not change the period. Weights released 5 and 10 centimeters from equilibrium complete their oscillations in the same time. The larger trip brings proportionally larger accelerations and speeds, exactly compensating for the extra distance. That is our two-tunnel race. Earth's radius is the amplitude for the diameter tunnel. Half a shallow chord's length is a smaller amplitude. But both obey it equals minus g over r times x, so both share the same angular frequency, the square root of g over r. The time for a full oscillation surface to opposite surface and back is 2 pi times the square root of r over g. A one-way trip is half that, pi times the square root of r over g. Use Earth's radius, about 637 million meters, and surface gravity, about 981 meters per second squared. The square root is roughly 86 seconds. Multiply by pi, and we get about 2,502 seconds, 4,202 minutes. No tunnel length appears. That is the cancellation in its final, rather lovely form. A shorter chord reduces distance, maximum acceleration, and maximum speed in precisely the same proportion. But before we congratulate Earth for its punctual railway, our model smuggles in a lie. Earth is not uniformly dense. Real Earth puts much more mass near the center than near the surface. The core is dense, iron-rich material. The mantle is less dense. As a capsule falls inward, removing outer shells still works if we treat Earth as concentric layers, but the remaining sphere is not a uniformly shrunken Earth. Near the surface, gravity initially increases slightly as you descend. That sounds backward, but distance is not the only change. You discard low-density outer material while approaching a dense interior. Deeper down, gravity decreases, reaching zero at the center as symmetry demands. The restoring acceleration is no longer a straight line in x. Our planetary spring is nonlinear, and the equal time miracle breaks. Run the tunnels again with a layered Earth model. The diameter capsule arrives in roughly 38 minutes, not 42, because stronger interior gravity gives it a serious boost. Shallower chords stay closer to the uniform Earth prediction, while different tunnel depths produce different travel times. The spread is modest, but exact equality is gone. Earth also rotates. Except in a tunnel along the rotation axis, a falling capsule retains sideways motion from the surface and drifts into the wall, unless guided. Add air resistance, heat, pressure, and the slight issue that rock closes holes, and this is not a construction proposal. But those failures reveal what was mathematically special. Equal time came not from spherical symmetry alone, but from uniform density, which made interior gravity linear, and every straight chord the same oscillator at a different amplitude. So straight tunnels lose their perfect timetable on real Earth. Could we change the tunnel shape and recover something even faster? A curved tunnel can beat the straight chord between the same two cities. The winning path dips steeply at first, gathers speed early, then turns toward the destination. It is the underground version of choosing a longer slide because the first drop is sharper. Compare two tracks between nearby surface points, the straight chord, and one bowing toward Earth's center. Though longer, the curved track plunges, gathers speed early, pulls ahead, and arrives first. This is the brachistochrone conflict. Shortest and fastest need not coincide. In constant downward gravity, the fastest curve is a cycloid. Inside Earth, gravity's direction and strength change, so the optimum depends on the density model we cannot paste in the textbook cycloid. For a uniform Earth, imagine the capsule not as a train, but as part of an orbit through the planet, governed by the same central force. Constrained straight chords all yield 42 minutes, while unconstrained orbital arcs show how dipping inward trades extra distance for earlier speed. Clever routing has limits. A diameter already dives as deeply as possible, so antipodal points offer no deeper shortcut. For close cities, the chord stays shallow and slow, leaving room for a curve to improve it. Notice what changed. The first mystery asked why wildly different straight tunnels tie. Not because path length never matters, length and acceleration mattered, scaling together under one specific force law. Once the path redirects gravity, that cancellation no longer controls the race. Which leaves one last question: can we see the equal time result without following a capsule through a tunnel at all? Take an object moving in a circular orbit just above the surface of our uniform Earth. Its speed is the familiar square root of g times r1 orbit takes 2 pi times the square root of r over g, about 84 minutes. That number should look familiar. A gravity train trip takes exactly half of it. View the orbit edge, on. The orbiting point circles Earth, but its shadow on any diameter slides back and forth in simple harmonic motion. During half an orbit, the point crosses from one side of the circle to the other, and so does its shadow. 42 minutes. Rotate the projection line or shorten the shadow's amplitude. The timing stays unchanged. Every coordinate of uniform circular motion oscillates with the same period. That shadow is the mathematical twin of a capsule in any straight Earth tunnel. Here is the cancellation in one picture. A long tunnel is a large shadow motion, farther to travel, but greater projected acceleration and speed. A short tunnel is a small shadow motion, less distance, acceleration, and speed. Both follow the same invisible angle, sweeping around the circle at a constant rate. Of course, a real satellite would hit mountains, a real tunnel would hit several engineering departments, and Earth's density varies. But within the ideal model, the timetable is exact. Return to our two capsules, one falling nearly 13,000 kilometers through the center, the other following a modest chord between nearby points. They are differently sized projections of the same oscillator. Release them together, and one hidden orbital hand carries both between endpoints. Half a revolution, 42 minutes. Every straight tunnel, right on time.